A wire having a uniform linear charge density lambda. When we have a uniform, it means lambda is constant. And it has this shape. Find the electric potential at the point O. You know, V total created at the point O equals, here we cannot take all the system one time directly. We have to calculate the electric potential created by this part. This one, the left part, equals to VL, plus the right part equals VR, plus the semi-sphere Vs. So V here, VO, equals to the electric potential created by this one plus this one plus this one. Okay? Here, to calculate each one, you know, I have to take a small element from each side. The most important point here, how can we take the x-axis of the system? You can take x and y, maybe like this, and at the origin. Okay, first case, at the origin. Or you can take the y-axis at this point. But you have a big difference between this position and this position, because if you put here the x-axis, the y-axis, so the x to the left must be negative, and the x to the right must be positive. But if you put the y-axis here, here you have only the positive value of x. We don't have negative, only the positive value. Let's take, I want to solve the problem with the two cases. First case, if we have the x first at this point. Okay, so I take the first case when we have the x at the origin O. Okay, here we take, first of all, I want to calculate V left. For the left part, I want to take dx because this road is along x-axis. So we have dx. And this part is located at the negative minus x, at minus x. Okay. First of all, I have to put the distance between O and dx. And second, here we have dq. dq will create at the point O dv equals to k dq divided by the distance between dq and the origin. The distance between dq and the origin equals to minus x. You see here, in the case of a continuous object like this one, you need to take the negative position and the positive position. You cannot take only the absolute value. Here we have minus x. The integral to calculate VL equals to, you know, dq equals to lambda dx. So here we have k. We have k is constant, lambda is constant. The integral of dx divided by minus x. You can put minus x here, or you can put minus here and x down. About the limit must be from the negative value toward the positive value. Let's say from the point A to the point B. The same for this road. I take from the negative value toward the positive value, from C to D. So here I take from the position of A to the position of B. And you have here only one variable, X. X must be from the position of A to B. A is located at 2R plus R. So we have minus 3R to the point B, which is located at a distance equals to minus R. Okay? So we can say here the limit of the integral will be between minus 3R to minus R. Okay, it's clear now. Between this point to this point, minus 3R to minus R. Okay, here we get minus k lambda. Integral of dx divided by x equals to ln x. Okay, so here we have ln x between minus 3R to minus R equals to minus k lambda ln minus R minus ln 3R ln A minus ln B equals to ln A over ln B. So we can write minus k lambda ln minus R divided by minus 3R minus, finally we get minus k lambda ln, we can eliminate minus and minus, R and R, we have ln 1 over 3R. Here we can write, we can eliminate the negative and we change this one. So we get k lambda ln 3. You know, ln A equals to minus ln 1 over A. Okay? Why? Because ln minus ln A equals to ln A minus 1 equals to ln 1 over A. Okay? Okay. Finally, we get here V at the point L equals to K lambda ln 3. Let's now calculate V right. V right, also we have the x-axis and y-axis, the same one, and we take a small part of the road along dx, which is located at the position x from the origin. Here we have x. Okay, now I want to calculate V right. dV is created by dq at the origin equals to k dq divided by the distance between dq and the origin. equals to x. Okay, to calculate v right, we do the integral equals to k lambda dx divided by x, and here x, if we move the charge from this point to this point, so it must be between this point and this point. This point is located at R, and this one at 3R, okay? Between R and 3R. Between this point and this point. Here we have R, and here we have 3R. Equals to K lambda ln 3R divided by R, okay? Equals to K lambda times K lambda times ln 3. So V right equals to the same value as V left. Okay, it's normal because we have the same quantity of charge at this position and at this position. They will create the same electric potential at the origin, as if you have, for example, a positive charge Q and the same positive charge Q. At the origin O, we have V created by the first one plus V created by the second one, the total V at the origin. So we have the same sign, the positive value. So V total equals to K Q divided by the distance here plus KQ divided by the distance. You get the same value from this side and from this side. In the case of a point, we don't need to put minus and plus, okay? We don't need. But in the case of a continuous object, we have to put minus and plus, minus r, minus position, because you have an integral between 2 points. We need to put x-axis and y-axis, and we put minus x plus x, and you solve the problem like this. But in the case of a point charge, we don't need. We can put it directly. Okay, let's continue. Now I calculated for these points. Now we have the semi-sphere, this one. Also, we can take a small part. Here we have dl, because it's not dx, it's not dy, it's dl. And we have dq on dl. Look here, you know, v, it's not a vector quantity, it's a scalar quantity. We don't need to put a symmetric and x and y components. We have only x, we have only scalar quantity without direction. So dq will create at the origin dv, which is located at r. We can say about vs, dv is created by dq at the origin equals to k dq divided by the distance between dq and the origin equal to r. Okay, so we put the integral, we get vs equals to k lambda dl, because dq equals to lambda dl divided by r. R is constant. If you move dl from here to here, the position of dl with respect to O must be constant, equals to r, capital R. So we can put r outside the integral. We get finally k lambda divided by r integral dl. Here you can solve it like this. First of all, you know the integral of dl equals to L. You can write k lambda divided by r times L. Okay? And you know L from here to here. You know, if we have L like this with an angle equals to theta with a radius r, L equals to r theta. In this case, L equals to r theta, theta equals to pi. So we can write here equals to k lambda divided by r times L equals to r times theta. So we get finally Vs equals to, we can eliminate r and r, equals to k lambda times, excuse me, we have lambda equals to r theta and theta equals to pi, okay? We can say here pi. Excellent, huh? It's good. Now, if you want to put delta L here equals r d theta, you can put, because if you have a small delta L is located with a radius r, and here we have an angle d theta, so dl equals to r d theta. So we put dl equals to r d theta, and theta between 0 to pi. You know, theta from this point to this point. If you move delta L along the path of the wire here, you have theta between these 2 points. So we have theta between 0 and pi. And pi, not 2 pi, pi. R is constant. We can get out here we can write k lambda r divided by r integral of d theta between 0 and pi equals to k lambda theta between 0 and pi equals to k lambda pi. We get the same result. So like this, we calculated Vs created by the semi-sphere equals to k lambda pi. We can write at the end the total potential at the point O equals to Vs plus V left plus V right equals to 2 k lambda ln 3 plus k lambda pi. We can take k lambda 2 ln 3 plus pi. This is the answer. You can we can do the same calculation if you want, if we put the y-axis at the edge of the wire at this point, and we can do the same calculation. Okay, so the second method, if someone wants to solve the same problem but you put the x-axis and y-axis at the origin or at the edge like this. Okay, let's calculate each one. You know, VO equals to V right plus V left plus VS. Let's start with V left. We put a small part of dx and we have dq. This dq is located at a distance x from the origin here we have x. Here we have x. Okay, we have x, and you know, dq will create at the origin. I need at the origin, okay, at O. Here we have, if you want, we can say here point P, because I need to calculate the total electric potential at the origin at this point. And here I think, okay, anyway, we can keep it O. Okay, here we have O, and here we have the origin. Okay, dV is created by dq at the point O. Okay, you can say point O, point A, point P as you like, but it means at this position, equals to K dq divided by the distance between dq and the point where I want to calculate the total electric potential. The distance from dq to this point equals to the total distance 3r minus x. Okay, so the distance between dq and the point equals to 3r minus x. Okay, I want to calculate v. Okay, here I need some calculation of integral. Okay, it takes time, but you can do it. Anyway, VL equals to K lambda. Inside we have dx divided by 3r minus x. As you see here, we have only one variable. The variable is between. Here you have to move dq along the road, and x will be from this point where x equals to 0 to this point where x equals to 2r. Okay, from 0 to 2r. And here I have to calculate the integral. You know, to calculate this integral, you take u equals to 3r minus x delta u over dx equals to minus 1. So you can say du equals to minus dx, or we can say dx equals minus du. Okay, so here we can say k lambda, and we have to change the limit. Dx equals to minus du divided by u. You know, the integral of du over u equals to ln u. We get minus k lambda ln u, and now you can put u here equals to minus k lambda ln u equals to 3r minus x between 0 and 2r. We get here minus k lambda ln 3r minus x equals to r minus ln 3r minus x. So we have minus k lambda, 3r minus 2r equals ln r minus ln 3r equals to minus k lambda ln r divided by 3r. Okay, we can eliminate this one and this one. We can put here plus, and we change 1 over 3. We get minus or plus k lambda len 3. As you see, we get the same value of v left we calculated before. So here we have v left equals to k lambda len 3. We do the same calculation for the right side. Okay, and here we have x-axis at this point. We have to take the same x-axis and y-axis. And here I take the right one, v right. I take a small portion here, dx, the position of dx with respect to O, not O, the origin, equals to x. Here we can put x. And dq, I want to calculate at the point O. You know, at the point O here, the electric potential. Here we have dq. dq will create at the point O dv equals to k dq divided by the distance between dq and the origin O. Not this one, at the point where I want to calculate the potential. This distance equals to the total distance, this one, minus this one. The total here equals to x, as you see, equals to x, minus this one equals to 3r. Okay? So we have x minus 3r is the distance, this one, from the point to dq. Now, I want to calculate v right equals to k lambda integral dx divided by x minus 3r, and we put the limit. The limit you have to move. Here we have point A, we have point B. We move the charge along the road from this point to this point. Okay, so the point A is located at 2 plus 2r, so at 4r, and point B is located at 4, 5, 6, at 6r. So between 4r to 6r. Okay, this is the limit of the integral. Now, in order to calculate this integral, you have to do the same procedure. You take u equals to x minus 3r. So du divided by dx equals to 1. So du equals to dx. So here we get du divided by u integral equals to len, we have k lambda here. We have k lambda. Len u equals to x minus 3r between 4r and 6r. So we get here k lambda len x equals to 6r minus 3r minus len, we have 4r minus 3r. Okay, we get k lambda 6r minus 3r equals to 3r, 4r minus 3 equals to R. So we get finally len 3. So we have V left equals to K lambda len 3 and V of the right side equals the same value. Okay. Now it's the time to calculate this one. Okay, we can follow the same procedure here. We take dl and we have dq at this point. Here we follow the same procedure. We cannot we don't need to take in terms of x-axis. Okay. Anyway, let me continue the solution. We have x-axis, we have dl. You know this one is located at a distance r, so dv, I want to calculate v created by s. dv equals dq divided by the distance. We calculate vs equals to the integral of k is constant, lambda is constant, r is constant. We have inside only dl. Okay, so vs equals to k lambda divided by r times l, and l equals to r times pi, so equals to k lambda pi. Finally, vo equals to 2 k lambda times len 3 plus k lambda pi. We get the same result if you put the x-axis at this point or at this point, but be careful about choosing the x-axis and y-axis and how you can calculate the position in terms of the y-axis.